Okay, so now let me go back to the thermodynamics of irreversible processes. And I think we stopped at this slide. Okay, so as I mentioned then, the production of entropy is just sum of all the flows times the forces of all the irreversible processes which are occurring within the system. This has to be greater than zero by the second law of thermodynamics. And we also have the possibility of coupling of two different irreversible processes. So for example, the flow of matter could be due to the concentration gradient plus also a heat gradient that will also give rise to a flow of matter, because you know the density of the material changes as a function of temperature. So we have a possible coupling of two different irreversible processes, and then we have these coefficients which determine the relation between the different forces and the flows. So this could be the flow of material, and this could be the force due to the differences in the concentrations, and this could be due to the differences in the temperatures, and that gives rise to a flow of material. And and the second one would be the flow of heat, which could be related to also the gradient of the concentrations and the gradient of the temperatures. And then if we plug these values, this linear relation between the flows and the forces, into this equation for the entropy production, then we get an equation of this form, which has to be greater than zero by the second law of thermodynamics. And now to satisfy this relation for whatever values of the x, the forces here, we need that these on-cycle coefficients, the proper coefficients, L11 and L22, have to be greater than zero. We also require that L12 plus L21 squared has to be less than 4 times L11 times L22. And these criterion can be derived from this equation, knowing that it has to be greater than zero, and taking into account that we can have whatever values of x here, it always has to be greater than zero, because that is the second law of thermodynamics. So we also have on-cycles, what are known as on-cycles reciprocity relations. That means L12 is equal to L21. So these cross coefficients here are equal. And that can be determined or shown by microscopic reversibility. So at the microscopic level, we have reversibility. And that gives rise to the fact that these on-cycle coefficients have to be equal. These are the cross coefficients. So assuming that we have linear phenomenological laws, these phenomenological laws describe the relations between the flows and the forces. And if we assume that we have constant phenomenological coefficients, these are the L11 and the L22 and the L12, L21, these coefficients. If those are also constant, then we can show that the production of entropy is a minimum with respect to the variation of the forces, the free forces in the system. So we can show that the partial derivative with respect to the force, J, of the entropy production is equal to zero. It's an extremum. And in fact, we can show that it's a minimum. And that is in the book of Prigogine. So I'm not going into the details here, but it's all derived in the book of Prigogine. So please try to read chapters 1 to 3. So that's saying that if we take any system out of equilibrium and we watch the system over time, we will, and the system is linear, okay, then we will always find that the entropy production decreases as a function of time and goes to its minimum value. And that's in the stationary state. So to give an example, let's say that we have an iron bar, which is separating two reservoirs, one at temperature T1 and the other at temperature T2, which is greater than T1. then we know that heat will flow from this side of the bar on the right side into the lower temperature, T1. So initially the bar will be at a uniform temperature. Let's say the temperature of the environment, and we connect it to these two reservoirs of different temperatures, then we will start to get a heat flow. And we can measure the temperature at any point along the bar, and it will be changing until we give it sufficient time that the temperature at any point becomes a constant value. That's known as a stationary state. And then we will have a constant flow of heat. But that corresponds in that stationary state to a minimum of the entropy production. That is the case that we have linear phenomenological laws, which is not the case of life. Life has nonlinear laws between the flows and forces, and that gives rise to the fact that the entropy production can in fact increase in time. So under these conditions that we do have this linearity, then the entropy production as a function of time has to always decrease. It's negative definite. dP by dt is negative definite. However, we know that the entropy production has to be positive. So this is the entropy production. This is the change of the entropy production as a function of time. So the fact that you have a function here, which is positive definite, that's by the second law of thermodynamics, that the entropy production is positive definite, and its derivative in time is negative definite, implies that you have a Lyapunov function. And for those of you who have studied mathematics, when we find a function of this form, that its value is positive definite, but its time derivative is negative definite, we can show that this corresponds to a stable state. So in this case, we have a stable stationary state. So that means if there are fluctuations, that the system won't change. It'll go back to its original stationary state. So again, taking the example of a metal bar connected between two reservoirs of temperature T1 and T2, and looking at any position on the bar, measuring the temperature, when we first connect the bar, the temperature will be changing until we get to the stationary state. Then the temperature will be fixed at a given point on the bar. It will be different at different points, but it won't be changing in time at any point. Okay, and that's the stationary state. And that corresponds to a minimum of the entropy production. That's what Prigogine showed. I think it is in chapter 3. Okay, but that doesn't tell us anything about nonlinear phenomenological laws that we're going to get into the following days. But that's all I had then on the first 3 chapters of Prigogine. So if you haven't read those chapters, please read those chapters. Okay. Now let me go to, if there's any questions, let me answer them. Give me some questions, please. And if not, I'll go to another talk I wanted to present, which is that the origin of life actually occurred on the ocean surface.
That's interesting, because I was about to question you that, because I was thinking the exogenous delivery, like in interstellar space, like, I don't know, imagine like a simulation how we are doing, but in space. But I think that maybe it's not possible because the temperatures are very low, no?
Well, in fact, they have found many molecules of life in space. I think they're now something close to like, well, maybe 50 fundamental molecules of life have been found in space, including the amino acids, nucleic acids, and even some of the fatty acids, the short chain fatty acids. So they have found these molecules. They can be produced in space. And we believe that they can be produced in space because of the same fundamental thing, which is dissipative structuring under ultraviolet light from the stars. Okay. There are some problems because, for example, if we have very short wavelength light, we can destroy these molecules. So they cannot occur in every region of space. They have to be shielded from shortwave radiation, ultraviolet radiation, which can destroy them by ionization. So, but they have been found in different regions, and there are different types of stars which produce only small portion of the ultraviolet light because their surface temperatures are not hot enough to produce the very short wavelengths which can ionize the molecules. So we believe the same thing is happening in space. And in fact, on meteorites also, they've found organic molecules. The reason that the meteorites are very black, very absorbent of all light, we believe is due to the formation of these organic molecules, which are specifically produced through dissipative structuring to absorb the sunlight on the comets and meteorites which go around the sun. So for example, when a comet comes in from very far out of space, when it gets close to the sun, it starts to melt. Some of the ice melts and we get water and water vapor. And with this water and these precursor molecules like hydrogen cyanide, for instance, we can produce these molecules on the surface of the meteorites with ultraviolet light from the sun. Some of it, of course, is going to be destroyed because the sun also puts out these very short wavelength light. So they can be produced in space, but it's not necessary that we have transport from space to Earth because they can also be produced on Earth's surface. And as I mentioned, what is important is not the production, because there are many ways to produce these molecules. You can use ultraviolet light, or you can use heat, or in even some cases with a pH or an acid gradient, pH gradient. So there are many ways to produce the molecules. You don't need ultraviolet light. But life is much more than just the production of arbitrary molecules. It also has this vitalism, this dynamics to it, which can be seen in metabolism or in evolution or in the dynamics of movement. So this dynamics also has to be explained. You can not only explain the molecules of life and then hope to have a good theory for the origin of life. You need to be able to explain the dynamics, and the evolution of the system, which is part of the dynamics. And to have this dynamics, you need a continuous supply of free energy. And for example, at hydrothermal vents, you don't necessarily have a continuous supply. They might last only for 100,000 years. Or for example, if you're producing them through lightning, the molecules through lightning, which was the production mechanism of Stanley Miller, but lightning only is there exists for a very short time. Then you no longer have free energy. So you couldn't get to the vitalism or the dynamics of life. You need a flow of constant free energy, and that the only flow of that available is in the photons, which are coming from the stars or our sun. I'm not sure if that explained your question or answered properly your question, Claudia.
Sorry. Well, yes. También, perdón, es que como que de repente no me puedo expresar muy bien en inglés.
Sí, está bien en español igual.
Pero por ejemplo, no sé, si tenemos un cometa que pasa muy cerca de una estrella, y ese cometa tiene hielo, se derrite, ahí tenemos agua y con luz ultravioleta. Pero ahí mi problema sería que no, el paso del cometa sería como demasiado rápido, tanto que no iba a dejar que se desarrollaran las reacciones químicas hasta llegar a compuestos. O sea, es lo que me intriga.
Pues, por ejemplo, sabemos de nuestros cálculos que en 30 días, con estas reacciones fotoquímicas, pudimos producir una cantidad de adenina suficientemente grande para ser medible, ¿no? Entonces, si tienes luz ultravioleta y si tienes los precursores que son agua y cianuro de hidrógeno, 30 días parece más que suficiente, por ejemplo, para producir arenina. Y los cometas, cuando hacen la vuelta a la Tierra, dependiente de su trayectoria, por lo menos tienen meses, ¿no? Cerca del Sol, cuando están suficientemente cerca para que tienes un flujo constante y importante de luz ultravioleta. Y a distancias más largas, entonces ya puedes tener menos agua, quizás si es en estado sólido, pero todavía puedes producir esos moléculas aún en hielo. También se conocen porque unos granos que están en el espacio entre estrellas parecen que sí tienen moléculas orgánicas. Entonces tampoco es necesario agua en forma líquida. Entonces aún a distancias muy lejos del Sol, se puede con la luz ultravioleta estar produciendo estas moléculas orgánicas. Pero a partir de ahí la evolución, ¿no? En sistemas más complejos de distintas moléculas orgánicas, ya es mucho más difícil. Sin el agua en forma líquida y sin un flujo constante y importante de luz en el UVC. ¿Ok?
Y en el espacio hay HCN.
Sí, HCN de hecho es una de las moléculas más común en todo el universo. Lo encuentras
Ok.
cada espacio. Es la que hay más, yo creo que más de agua, que hay de agua. No sé si es el segundo o la tercera, ya no me recuerdo, pero es una de las moléculas más comunes en el universo. Hay que ver si no el cianuro de hidrógeno no también fue resultado de síntesis por dissipative structuring, ¿no? Estructuración disipativo en un rango de frecuencias más cortas o más largas, frecuencias más cortas en longitud de onda, en un región distinto de la ultravioleta. Pero sí es una molécula muy común en el universo. Ok, entonces déjame ir a esta plática que es sobre la superficie del océano como el cuña de la vida, okay? So the ocean surface as the cradle of life. So at the origin of life, we assume that we had shallow seas because there was not very much formation of continent at that time. So most of the water that existed on Earth at that time would have been dispersed. So we would have the seas a little bit shallower than they are today, and very little land area. The atmospheres contained carbon dioxide, nitrogen, water, methane, and probably some hydrogen. This methane and hydrogen come from serpentinization, which is a chemical process using metal catalysts on these other molecules like carbon dioxide, nitrogen, and water. You can produce methane and hydrogen in small amounts. And there was also this ultraviolet light, as I mentioned, because there was no oxygen, so there would have been no ozone. And the Earth's surface temperatures were hot, 80 to 85 degrees centigrade. And we had more radioactivity, which implied that there were more volcanoes. And therefore, we had also more hydrothermal vents at the bottom of these oceans. We also assume that we have more asteroids and more comets, which could have been providing Earth's surface with this organic material, but not necessarily, because as I mentioned, we can also produce it on Earth itself. So life then is a process which dissipates free energy, and we're assuming that it's starting with ultraviolet light. So let's compare the amount of free energy due to different sources on the surface of Earth at the origin of life. So this is a calculation, or really a compilation of different results from different people who have studied this. So for example, in the solar radiation, in the visible, let's say greater than 300 nanometers, we have 2.6 times 10 to the 6 kilojoules per meter squared per year of free energy. Okay, this is due to visible light, basically visible. This is a little bit in the ultraviolet. We also have solar radiation in the UVC in this range that we needed for the production of the molecules of life at 230 to 280 nanometers of about 3.9 times 10 to the 4 kilojoules per meter squared per year. Now with lightning, we have only 1.9 times 10 to the 3. So we have more than an order of magnitude less free energy in the lightning that could have been occurring at the origin of life. Coronal discharge, well, that's also involved in the lightning. We have about 9.8 times 10 to the minus 2. And we also have free energy in the shock wave of impacts, because this is another theory that the impacts of the meteorites, which were occurring more frequently at the origin of life, could have provided the free energy to produce these molecules, because they have also been produced in the laboratory using shock waves, okay, impacts to produce shock waves, which create these molecules of life. And we also have this radioactivity, okay, and this radioactivity is due to atoms which are heavy, so like uranium, which are decaying, and they provide a certain amount of free energy. That is what was keeping the Earth warm for a long period of time, still is keeping it warm, and that's producing the volcanoes. And the actual energy which comes out of the volcano, only about 5.4 kilojoules per meter squared per year. So by far, the amount of energy being received on Earth's surface is that due to solar radiation in the visible. But we know that these wavelengths in the visible are not strong enough to break and remake carbon covalent bonds. That energy is only available in the UVC range, about 230 to 280 nanometers. So of all the free energy sources on Earth at the origin of life, the one which is by far the greatest is the solar radiation in the UVC. Okay, and there's also a calculation which was done by Miller and Urey. It was published in Science, which basically says the same thing. So the volcano and the lightning are very small compared to light in the UVC. Yes, yes, Ricardo.
Sorry, and at this time, the Earth's magnetic field, what?
Oh, okay. It would have been even stronger than today. Why?
Yes.
Because the Earth would have been warmer. So we would have had the interior being more liquid. The metals in the interior would have been more liquid than they are now. And also the Earth was rotating rapidly. So at the beginning of life, at the origin of life, a day was about 16 hours compared to 24 hours today. So it was spinning more rapidly, and the liquid core was more liquid. So we would have had a greater magnetic field, which means that the particles coming from the sun, well, in fact, this is the coronal discharge, particles, would have been even less than today, because they would have all been channeled towards the poles, towards the magnetic poles. So in fact, that energy coming from the sun in terms of particles, in terms of charged particles, would have been very small also, as we see here now. Okay.
Yes, thanks.
Okay. So now let's talk a little bit about hydrothermal vent hypothesis for the origin of life. What are some of the positive reasons and some of the negatives? So in the list of positives is that temperature and pH gradients are a source of free energy. So actually some of the water coming out of these vents, hydrothermal vents, is at very high temperature, about 400 and 500 degrees centigrade. So there's a gradient of temperature because the ocean temperature is about 4 degrees centigrade at the ocean bottoms. That means at about 5 kilometers depth, we have about 4 degrees temperature over the whole ocean surface, the bottom. And we have 500 degrees of this hot water coming out of these hydrothermal vents. So this gradient of temperature can also provide free energy for the formation of these molecules. We also have pH gradients because some of the dissolved minerals in the water coming out of the vents have a different pH. You know, they can be basic or acidic, but they're basically basic with respect to the water in the environment. So we have also a pH gradient, which could also be used to form these molecules. So these are the sources of free energy. And we also have a lot of metals also, which are coming out of these hydrothermal vents. This water, in fact, is in fact the ocean water, which is being subducted in the subduction regions, which are far from these, well, not too far from these hydrothermal vent regions. So for instance, we know that our volcano Popocatépetl is producing a very similar concentration profile of the different elements to those of the ocean, because it's the ocean water which is being subducted and then being taken out through these volcanoes, which can occur at the bottom of the ocean floor and they become these hydrothermal vents, or they can occur on the surface of Earth and these give rise to these volcanoes. So we have these mineral catalysts, these metals also, which are coming out of these vents, which can be considered as catalysts for some of these reactions. And we also have protection from UVC light because many people, or they still do, in fact, claim that this ultraviolet light in the UVC is dangerous to life. And it is, in fact, dangerous to develop life with proteins, but it's not dangerous to the fundamental molecules of life. So, but they give that as a positive reason that there's no UVC light at the bottom of the oceans. The negative aspects of this theory or hypothesis is that they have done these experiments in the laboratory. So they have reproduced the pressures of the ocean water and reproduced these hydrothermal vents in the laboratory, but they find very little organics being produced. So we do get some organics, but we have never found, for example, the nucleic acids being produced on these hydrothermal vents. And in fact, the life that they found around these hydrothermal vents, they assumed at first instance that they were using the energy, the free energy in these hydrothermal vents to survive, because they have found a lot of life, even very big creatures like crabs and things like that, which are living at very low depths, minus 10 to the 5 meters, or not so much, but at least 10 to the minus 4, 10,000 meter depths. And so they assumed that these hydrothermal vents could provide this free energy in the form of temperature gradients and they also giving out a little bit of light in the infrared, which can be used by some cyanobacteria, which can survive at those temperatures and those depths. But studying the system more carefully, they're realizing that most of the life around the hydrothermal vents is not living off this temperature or pH gradients. They are in fact living off the material which is coming down as rain is falling into the bottom from the surface of the ocean. So the life on the ocean surface, which is using light to survive and reproduce, when it dies, it's gradually being raining down to the ocean surface. And it's been found that those organisms which are living near to hydrothermal vents are in fact living off the dead organisms which are floating down to the bottom of the ocean. And we also know that, as I mentioned, the water which is flowing out of these hydrothermal vents is being subducted in the subduction zones, which are at some distance from these hydrothermal vents. So in fact, all the ocean's water are being recycled